In the order to optimize the performance of our solar panels, we need to point them in the direction that maximizes the incident irradiation. In the previous video, we discussed the three different components of light: direct in red, diffuse in green, and albedo in orange. We derived the expressions for these components as a function of the tilt and azimuth angle of the PV module. So now the goal is to find out for which module tilt and azimuth the annual irradiation on the module is maximized. We will therefore focus on two optimization concepts: a fixed panel and a panel with mechanical tracking. In this video, we will especially focus on finding the optimal tilt angle for a fixed panel. First, however, we will discuss the optimization flowchart to get a better understanding of the procedure used to obtain the optimal tilt angle. A rule of thumb for quick optimization is to use an angle equal to the latitude of the location, facing south in the northern hemisphere and the north in the southern hemisphere. However, the most common way to find the best combination of tilt and azimuth is to simulate the performance of the module. Before going into the simulation, we have to distinguish between the two possible configurations to mount PV panels. One possibility is to use a fixed panel where you can choose the tilt angle and maybe adjust it a few times during the year. Alternatively, a mechanical tracking panel configuration could be used that follows the sun during the day. This will be the topic of next video. So let's break down the fixed mounting systems a bit. The PV panel can have a constant fixed position throughout the whole year. This occurs, for example, in a residential photovoltaic system. We can also have a system with an adjustable tilt angle. Indeed, the further we move away from the equator, the larger the difference between summer and winter irradiance becomes. Therefore, a seasonally or even monthly adjustable PV system will achieve a better performance. Let's start to calculate the optimum tilt angle for a panel with a fixed position over the entire year. The best combination of module tilt and azimuth angle is found using all the concepts we have discussed until now. The idea is to calculate the position of the sun for whatever time step you decide to acquire an accurate tilt prediction. The measurement interval can be every hour, 10 minutes, or even second, depending on the irradiance information that is available. After computing the azimuth and altitude of the sun with respect to the location of your PV system, you have to decide what range of tilt and azimuth angles to investigate. If you want to consider all possible angles, the tilt angle will range from 0 to 90 degrees. The range of azimuth angles can be the complete circumference of 360 degrees. Generally, you can limit the azimuth range to the path of the sun through the sky during the day, so from east to west. It is true, however, that over the last years there is a trend to install modules also on the northern facade of buildings due to the decreasing costs and the increasing financial incentives for PV systems. Some people, for example, have the financial means to completely cover their roofs regardless of its orientation. Therefore, clients might ask for information about the performance of PV modules with non-conventional azimuth angles. The next step is to integrate the incident power over time for the full range of tilt and azimuth angles. This way, we will get the energy incident over a year for a specific combination of tilt and azimuth angles. This provides us with a so-called contour plot. On the horizontal axis, we have the azimuth of the module, while on the vertical axis, the tilt angle of the module is plotted. We can populate the contour plot with the total amount of energy incident on the module in 1 year, as combination of tilt angle and azimuth. The point where the incident energy is maximal corresponds to the best possible mounting configuration for the panels for that specific location. Note that in some installations, the array tilt angle or azimuth angle is decided for you. This can be the case for sloped roof mounted systems. Moreover, if your energy demand is highest in the winter, then you can optimize the tilt and azimuth for the winter months. This will, however, inevitably lead to a suboptimal annual energy yield. In this animation, we can see the position of the sun at noon in London over the whole year. The optimal tilt angle of the module changes throughout the year as the position of the sun in the sky changes. The sun is high in the sky in summer and low on the horizon in winter. At the end of this simulation, the best fixed tilt angle is computed to optimize the annual energy yield. For London, this optimal tilt angle corresponds to somewhere between 35 and 40 degrees. As the animation points out, however, the energy yield could be even higher for solar panel with an adjustable tilt angle. So let's look at the solar panels with an adjustable tilt angle for a moment. Normally, the tilt of the modules can be adjusted either twice a year, so optimized for winter and summer, 4 times a year, which means that they are seasonally optimized, or even monthly, depending on the potential benefit to the energy yield. The same approach we used before can be used to find the optimal configuration for each season or month. In this case, the incident power is only integrated for a certain month or season rather than over the whole year. You can then find the optimal configuration for the selected period. This approach can easily be used for any time period. However, it is rarely employed for time periods of a month or shorter because the potential energy gain is very small compared to the labor required to change the orientation of the panels. So, what if we have a slanted roof with an orientation that is not optimal? Basically, you can either accept a suboptimal tilting and azimuth, or you have to introduce an additional change of coordinates. We therefore need to calculate the normal of the module in horizontal coordinates in case of coordinates with respect to the roof are given. In fact, we have to transform the module normal from the roof coordinate system to the horizontal coordinate system. If you want to see all the steps to obtain the module normal on a tilted roof, you may refer to Appendix E of the Solar Energy book. Time for a short recap. In this video, we have introduced the flowchart to obtain the energy incident on a PV module over an entire year for a specific set of tilt and azimuth. The result is this contour plot that graphically depicts the yearly energy incident for all possible module orientations. With this tool, we introduce the fixed and adjustable concept for energy optimization. In the next video, we will look at a more advanced technique that is mechanically tracking the sun.